morning. Okay, so before we proceed, does anyone have any questions? If I remember last week we were starting to get into the rotational properties of the nuclear spin interactions, and we were looking at this table, how the different spin interactions have different ranks with respect to rotations. With a picture of the symmetries being using the atomic orbitals as a way of visualizing that, where an s orbital has rank 0, p orbital has rank 1, and d orbital rank 2. And then the different interactions, so they have these different ranks, but also depending on which rotation we're talking about. So it's not really rigorous to say dipole-dipole coupling has rank 2. You have to say with respect to what sort of rotation. So and there are three different sorts of rotations here. There's what's called the space rank, which is the rotation of the whole molecular system. There's the spin rank, which is the rotation of the spin polarizations using radio frequency fields, usually. And the field rank, which is to do with the rotation of the external magnetic field as well. So, yeah, and then I started to talk, I think, about how to define, how to write down the mathematics for rotations using three Euler angles. Alpha, beta, and gamma, and how you can define those in a standard way, how two frames, the relative orientation of two frames can be defined using three angles. And then I started to talk about the actual reference frames which are used in the theory of solid-state NMR. Well, actually this theory is really very general, but this is the way it typically goes in solid-state NMR. That for each interaction, it has its own principal axis frame. So here, lambda here is used as a way of denoting a particular spin interaction. And then there'll be a set of Euler angles, which are called omega pm lambda, which govern how that principal axis frame is oriented with respect to a molecular frame. And then there'll be another set of Euler angles, omega mr, which says how the molecular frame is oriented with respect to the rotor frame, which is the sample holder, if you're doing magic angle spinning NMR. And then a set of angles, omega rl, which says how the rotor frame is oriented with respect to the laboratory frame, which has the magnetic field along the z-axis. So in general, there's a chain of three transformations to get from a principal axis frame of a particular spin interaction to the molecular frame, to the rotor frame, to the lab frame, and then in which the magnetic field has a fixed direction. And this type of chain is common to many different problems in NMR. So in relaxation theory, then you also have a chain of transformations, different liquid crystals, you have a chain of transformations and so on. So this mathematics is very much universal to the theory of NMR. I talked a bit about spherical tensors, which are objects which have defined rotational properties, which always look the same. And the main property is that if you rotate any spherical tensor of rank L, if you rotate the component M, through a rotation defined by a set of Euler angles, then you generate more components, but always of the same rank L, but you can have different components M. And you rotate them by these things which are called Wigner matrices. And what you'll see in this equation, and it will be apparent in the following equations, some of the mathematics of this gets quite sort of, at least superficially, it looks quite complicated. You have lots of transformations and so on. And it's wise to get into really good practice, which helps you keep your head during these transformations. What I think is good practice is always write things so that the indices chain together. So you see how I have M prime here, which chains together with M prime here. You can imagine these two M primes cancelling each other out, and then you're left with M, which is what you need on the other side. So you see this type of pattern again and again. And actually, if you write equations in a consistent way, then they more or less write themselves, in which things just chain together nicely. So let's have a look at these Wigner matrices. So these are the magic matrices which rotate spherical tensors. And they always have the same form. So this might be a Wigner matrix of rank L. So since a spherical tensor of rank L has 2L plus 1 elements, then the Wigner matrix is 2L plus 1 times 2L plus 1. It's a square matrix, 2L plus 1 on each side. And each of these elements is a complex number. And the way it works is as follows, so if you remember, this big omega here is actually shorthand for alpha, beta, gamma. It depends on three angles. And the way the Wigner matrices are defined, each element, so in row M prime, column M, is the product of three terms. And the first term just depends on alpha, the second term depends on beta, and the third term depends on gamma. And the first and the last terms are just complex exponentials of the alpha angle multiplied by the index M prime. And similarly for gamma. So that's always the same for all the elements. And then the one which depends on beta is usually written with a small d, that's called a reduced Wigner matrix, and those are real functions of beta. So let's just look at two of them. Rank 0, the reduced element for beta is just a number 1. That's all there is to it. So that just means that any rotation through beta just leaves things unchanged. And then rank 1, you have basically some trig functions for the for the 9 elements, which can be looked up in a text. There is actually a complicated but general but very complicated formula for what these look like for any rank. But usually we only deal with the lower ranks, 1, 2, and they can just be looked up in textbooks or generated in Spin Dynamica or whatever. You see you have cosine beta over 2 all squared and so on. So that's the rank 1 matrix. And then the most important one is the rank 2 matrix, which now has 25 elements. And you can see that it starts to get pretty complicated, but anyway, it's always the same. And there are some important elements, some which turn out to be particularly important. So the one right in the middle of the matrix, so rank 2, but component 0, row 0, column 0, the one right in the middle is this famous function, a half 3 cos squared beta minus 1. And that's characteristic of rank 2. And very importantly is when beta is the magic angle, this single element vanishes. And from that, all sorts of properties follow. So if we go to the full Wigner matrix, the big D, which depends on alpha, beta, gamma, all 3 angles, you can see how it works. For the 0, 0 element, then the 2 exponential terms are both 1, because the exponential of 0 is 1, so it's still the same thing. So half 3 cos squared beta minus 1. And then for some of the other elements, like this one, D2, 2, 2, the reduced element is this cos to the 4th beta over 2 function. And then one has these exponentials, one for the alpha angle and one for the gamma angle. Okay? Now, we saw that we don't, almost always one has a set of transformations one needs to go through in order to define the problem. And that's simply a matter of multiplying these matrices together. And the way it goes, again, if you keep the notation neat, then it's very simple. So the rank L matrix for transformation from A to C is just the product of the rank L matrix from the transformation from A to B and then from B to C. And to go from A to B to C to D, you just multiply 3 matrices together, always keeping the subscripts nicely chained together. So if one writes things that way, then basically the equations more or less write themselves. You just keep everything in nice chains. And then you just use the rule for matrix multiplication. So if you want the M prime M element to go from A to C, you have to go insert an index in the middle, call it M double prime, and sum over that. And if you need to go from A to D, then you need to stick 2 extra indices in the middle, but sum over those. But again, if you keep everything, the notation neat and organized, and you go A to B, B to C, C to D, M prime to M double prime to M triple prime, back to M, all the M double primes and M triple primes annihilate each other, leaving just M prime and M on the outside. And this is really the key for doing the theory, is to keep everything well organized. So the equations sort of more or less suggest themselves. So for example, to take a spherical tensor with its 5 components, to express it in the frame A, when you know it in frame B, is just to multiply by the Wigner matrix and let, again, the indices B cancel each other out, leaving just A. And we'll see some examples of how this works. So it looks fairly fearsome at first, but actually it sort of runs itself once you get used to it. So what are these angles if we're looking at magic angles spinning NMR? So we have the principal axis frame of spin interaction. So suppose we have some molecular structure. And the coordinates are written in some reference frame M, and that will then be the same for all the different spin interactions. So we keep that fixed to a particular molecule. But if we're interested in the dipole-dipole coupling between spins J and K, that will have a principal axis system with a z-axis along the JK vector. While another dipole-dipole coupling would have a different principal axis system with a z-axis along the KL vector. And we would define Euler angles relating the principal axis system of JK to the molecular frame M, and we'd need another set of Euler angles relating the principal axis frame KL to the same molecular frame M. Then we have a sample holder. A rotor frame with the z-axis along the rotation axis. So that frame is fixed with respect to the sample holder. Now in general, the molecular frame M won't be the same orientation as the rotor frame. That would require orienting the crystal in a very special way with respect to the sample holder. So in general, there will be another set of angles relating the molecular frame M to the rotor frame. And what's more, if you have a powder, which you usually have, a powder is basically represents a large number of different molecules, each with a different orientation of the molecular frame and the rotor frame. So basically you have a set of crystallites in the rotor with different orientations. And in fact, there'll be a large number of them in general, many thousands of small crystallites, each with different molecular orientations. So we have the molecular reference frame and the rotor frame. And then finally we have the magnetic field. Now we define a laboratory frame with its z-axis along the magnetic field. The rotor rotates with respect to the laboratory frame. So there's another transformation, and that one is time dependent because the sample is going around, or the rotor is going around. So the spin Hamiltonian in a rotating sample is time dependent because the interaction is defined. You can start at the principal axis frame of an interaction, that gets transformed into the molecular frame, that gets transformed into the rotor frame, and that gets transformed into the laboratory frame, but that transformation is time dependent. So the laboratory frame is defined with a z-axis along the magnetic field. Doing magic angle spinning, which we often are doing in solid state NMR. We have samples going around at angular frequency omega r. We define the rotor frame fixed with respect to the rotor. And the key point is that the transformation from the rotor frame to the lab frame is time dependent, and we can do that with the three Euler angles. So that's alpha RL, beta RL, gamma RL. But the way the Euler angles are defined, and this is actually where Euler angles start to be convenient, is that actually only the alpha angle is time dependent if you rotate about a single axis. And in fact, the alpha angle is just proportional to the rotation frequency times time. It turns out with a negative sign if you think about it very carefully. So that's the rotation frequency. Basically, as time goes on, then the angle you need to bring the frame back to the lab frame constantly increases because of the constant angular frequency. And then beta RL is just the angle between the rotor z-axis and the field. That's the beta angle, Euler angle, beta RL. And if you spin it to exactly the magic angle, then beta RL is the arctangent of square root of 2, which is the magic angle. And then finally, gamma RL. Gamma RL doesn't matter it actually represents, so if you imagine we have a static magnetic field, vertical, and we have a sample rotating. So the alpha angle is that rotational angle around the object itself. That's the one which is increasing in time. We have beta RL, which is the orientation between the rotor frame and the lab frame. Gamma RL is actually that angle. So basically, on an NMR spectrometer, if you put the probe in the magnet, if you would rotate the probe around the magnetic field, that would be the gamma angle. But actually in high field NMR, that never has any effect.
What are people talking about when they talk about gamma encoded pulse sequences?
Yes, that's something maybe when Marina takes over, she will talk about that. That is actually referring to this gamma angle here. So this angle, this is again 3 angles, alpha MR, beta MR, gamma MR. And certain pulse sequences have a property that they're not sensitive, or actually the phase of the NMR signal or some other property depends on the phase on this gamma angle, and that turns out to have some useful properties for certain types of pulse sequences. But I would say that's a little bit ahead of what we're doing now. But it refers to this gamma angle actually. So the mathematics of it basically is that we have a spherical tensor which we could write down in the principal axis frame, transforms the molecular frame. That's fixed for every molecule if we assume a rigid molecule which isn't moving around. So a molecule which is fixed with respect to the molecular structure, some molecular reference frame. And if we have a powder, each molecule has a set of orientations with respect to the rotor. But in general, there may be a huge number of possible MR transformations. Just because a powder contains many molecules in many different orientations. And normally computations of spectra have to average over those angles. That's called the powder average. So the powder average refers to this set of 3 angles. And then the rotor frame rotates in a very nice coherent way with respect to the lab frame to some simple angles. Alpha is simple, just depends on time and rotation frequency, and beta is just the angle between the rotor axis and the field. Yeah, so there's the molecular frame, which in principle can be chosen how one wants, but sometimes a wise choice can reduce calculation time if that's what one is doing. In principle, though, it doesn't matter. And then, as I said, a powder in a rotor is an ensemble of a large number of systems, each with a different value of omega MR. Now, if it's a powder, then this omega R is completely randomly distributed. Every value of omega R, MR is just as likely as any other value. But there are also cases where you have oriented samples. Suppose you take a fiber, like we saw last week, you stretch it, you orient the molecules in a certain way. and then you mount the fibre in the magic angle spinning rotor so it has a certain orientation, then omega MR wouldn't be completely uniformly distributed. It would tend to be more likely to have certain angles in certain directions because you've oriented the molecules. That's also a possibility. When one does computations, and this is true for basically all solid-state simulation programs, you have to, if you're simulating the spectrum of a powder, which is the usual case, you have to basically repeat the calculation for many values of omega MR. And then you have a little bit of a compromise to make, because a real powder contains typically a million separate orientations. All of those little crystallites, if you count them up, there's usually about 1 million of them. Well, if you repeat the calculation 1 million times, that's a lot of computationally inefficient. So usually one makes a compromise. One distributes the angles in some reasonably uniform way, and then sums over those computations. And there's various schemes you'll find in the literature for which sort of distribution of orientations you can go for. Actually, there's no really ideal way of doing this. It turns out that, for example, if you have a sphere, if you want to put 12 points on a sphere so that they're all equidistant from each other, there's a nice way of doing that. They're the vertices of an icosahedron. So, which somehow looks like this. You have two pentagons like that, something on top, and then these go nicely like this. Oops, something like that. Anyway, you have an icosahedron that's got 12 vertices. I think maybe the dodecahedron, I think it has 20. I'm not absolutely sure. But I think 20 is actually, so you can arrange 20 points on a sphere, so they're all nicely equidistant from each other. But suppose you want to do 100 points. Well, it turns out the problem's insoluble. There is no such thing as 100 points distributed evenly on a sphere. And actually this is called the golf ball problem, because when people manufacture golf balls, they put those little dimples on, which somehow improve the flight of the golf ball somehow. And golf ball manufacturers have been scratching their heads for decades on how to get their dimples nicely equidistant from each other. And there's actually no way to do it. You always have to make a compromise when you go beyond 20. So there's various schemes which are sort of popular in the field. These ones show what's called repulsion schemes, which are done simply by imagining that each point on the sphere has an electric charge, and then letting the computer minimize the potential energy so that the points sort of arrange themselves to get as far away from each as possible and as they can. If you take 168 points, then they arrange themselves like that. And it looks very uniform, but actually if you look in very close detail, you find it's not actually uniform. So when you do computations, then you basically can usually read in files which contain these sorts of orientations. This is another popular one, 3 authors which have names that initials Z, C and W. Actually you see at the top there's a bit of a weird hole there actually. You can just see it. So it's actually not a particularly good one. And there's some schemes which originate with a Russian mathematician called Lebedev. Actually, another thing you can do is is change the weights so that each point doesn't have the same weighting as the others. You can see the Lebedev scheme actually has some points which have only a low weight. They're like some little corrections. But anyway, this is the sort of technicalities of computations in solid state NMR. And actually the schemes which are shown here, they're really only appropriate for two angles, because the orientation of each point just depends on two angles, two polar angles. But actually in general you need three angles, because you have three angles in the powder average. And strangely, actually, this is still more or less an unsolved problem in computational theory, actually, is how to do this best. You would have thought it would be sort of tied up a long time ago, but somehow it's still a bit of an open problem. What is the really best way of arranging these angles? As it stands now, you simply read in some files, some angles from a file, or on a website or something, and you find the ones which you like best. Okay, so we have a dipole-dipole coupling. So this is basically what I showed here. You orient the dipole-dipole coupling with respect to the molecular frame. You might have a different dipole-dipole coupling which has a different set of angles relating to the molecular frame. If you have a chemical shift anisotropy interaction, that also has a principal axis frame which needs orienting, but always with respect to the same molecular frame. So if you have multiple interactions, you have many such transformations that all go into the same molecular frame. So here there are two dipole-dipole interactions between spins 1 and 2 and spins 1 and 3, and a chemical shift anisotropy, spin number 2. For each of those interactions, you run it down a whole chain of transformations. And remember, for each of those rank 2 interactions, each of these can be a 5 by 5 matrix with 25 complicated trigonometric functions in it. And the whole sort of chain of what goes on in a solid state NMR computation or theory sort of is set up here. And you see immediately that the theory, you see immediately maybe that when you read solid state NMR papers, then at least, especially the earlier ones, which don't really use spherical tensors, they look extremely formidable because they're full of page after page of complicated trigonometric expressions. But actually they all have the same common form. And what I like to do is try and bring out the principles of it without going into a great deal of details, which nowadays are handled immediately by Spin Dynamica or other software anyway. So Spin Dynamica will just write out these trig expressions for you if you need to do it. So actually I wanted to, so I'll go now on to the next set of handouts. Like that. Actually, before we proceed, does somebody want to ask something? Yeah.
maybe a short one. So how important is it in practice to choose this distribution of angles to divide the sphere in parts?
Yeah, it's like many things, well, so it's hard to give a straight answer to that, really. It depends on the algorithm, if you're doing a computation. Let's say the simplest algorithms simply add up the spectra for all of these different orientations. And then tendencies, they will generate sort of noisy things because the peaks will not always be in variable places. So basically what will happen is suppose one's trying to simulate a nice powder pattern that looks like that, then an algorithm which simply sums up the contributions from different angles. You know, the first angle will give a peak here, the next angle will give a peak here, and then basically it starts to build up, calculating thousands of angles. And then typically it starts to sort of look a bit like this. Then the more angles you add, then the better it starts to look. And then really there's little to it except to simply keep on going until you start to get something which looks attractive and see when it converges. But it will depend a lot on the problem. If one's doing, if one's simulating magic angle spinning NMR, then we have a set of spinning sidebands. And then it's a different sort of problem actually, because the first orientation will give sidebands here. The second orientation will also give sidebands here. And actually the magic angle spinning, actually the peaks always arrive at the same place for all orientations. So the only thing which one's calculating is the amplitude here. And then you need far fewer angles to do that accurately, actually, than this sort of problem. Then in addition, there are routines which, at least for simple spin dynamical problems, like calculating the static spectrum of a solid, there are routines which interpolate in a clever way. And then very, very quickly give you essentially a nice, pretty much exact calculation in with very few angles. And then in EPR, then there's a program, EasySpin, which does that very quickly. But that's not general, so it doesn't work for all spin dynamical problems. So at the moment, actually, it's a little bit of it's a bit inhomogeneous, the field. There's sort of some problems you need just to pile on heaps and heaps of angles. Others, there are clever interpolation techniques. Others work anyway with relatively small numbers of angles. And I think it's a bit of a confusing landscape, actually. People generally just sort of look at the problem they're dealing with, and my advice would always be to you just keep on getting a feel of the particular problem by adding more and more angles and seeing when it converges. But I would say in computational spin dynamics, it's a bit of an unsolved problem, and I don't think even spinach, I don't think has really got to grips with it much, I think.
If one could estimate like the smallest bandwidth in the data, like the sharpest feature in the spectrum, from that one can have the kernel width or so, which goes over the averages.
Yeah, I mean, yeah, you can obviously get convergence faster if you broaden the peaks a bit. And in fact, if they're infinitely sharp, then you need an number of angles. So it's a messy problem. These interpolation routines work very well, but they're not at the moment general to any spin dynamical problem. I think there are ways of actually getting a general routine, but so far it's never been implemented as far as I know. But actually what I want to get at really today is not so much the computational aspects, but actually to get down to actually writing some equations. So let's just take it a bit further. So we have our spin interactions, the different rotational signatures. And then let's look now at one particular interaction, the direct dipole-dipole coupling, which is space rank 2 and spin rank 2. And field we can omit. And actually the spin Hamiltonian for this, at least in high magnetic field, there's a little bit for, let's say, for the more experienced people here, that there's actually a step before this equation which I've sort of left out, which concerns this equation is actually after the secular approximation. So it's applicable in high magnetic field. I didn't want to complicate matters too much. So we have a dipole-dipole coupling between two spins, J and K. And we have a complicated equation involving two second-rank tensors. But I'm going to make the secular approximation. Which is true in high magnetic field. So this is true for 99.9% of NMR experiments. And then it's a really simple thing. It's just the product of two second-rank tensors one for the space part of the interaction, written in the lab frame, so what we have here is we have a subsample containing some molecules, and we have a magnetic field, and we orient the lab frame with a z-axis along the magnetic field. We have a space part and we have a spin part. But they both have to be written in the same laboratory frame. So these are second-rank spherical tensors. So this is the m equals 0 component of a rank 2 spherical tensor. And this is the m equals 0 component of a rank 2 spherical tensor operator. So space part, spin part. And that can be read off directly from that table in which we have 2 for space, 2 for spin, 0 for field. And actually that's it, that's the spin Hamiltonian. The problem is it's not yet maybe in the most convenient form. The problem is that if we have 2 spins, J and K, then it's easiest to define the space part of the interaction in the principal axis frame. Of that interaction, which has its z-axis along the vector between the 2 spins. So we're in the wrong frame, basically, as far as the space part is concerned. We're in the right frame with respect to the spin part, because we like to have that in the laboratory frame. So we have to transform a bit. But first of all, let's look at the tensors. So the rank 2 spin spherical tensor operator has 5 components. And this is the middle one. And actually that's the one which is the spin Hamiltonian in high fields. That's the T20 spin operator for the coupling between J and K. Is this bunch of spin operators here. And actually the other ones we can forget about, they don't appear in the equation in the secular approximation. Then we have the dipole-dipole coupling. Okay, so let me just write down what that was actually. So the rank 2, component 0, spherical tensor operator, is this 1 over root 6, 2ijz, ikz, minus a half ij plus ik minus plus ij minus ik plus. From the theory of spherical tensors, these expressions sort of fall out, but they can always be looked up. Actually, the dipole-dipole coupling between 2 spins has, you can see that there are 2 different parts to it. This thing is usually called a flip-flop term. Because this plus minus basically means that the coupling causes the 2 spins to flip each other, one going up and one going down. And then we have the space part, and in the principal axis frame, that's So in the principal axis frame of the same interaction, it is also a really simple thing. So there's 5 components to it. And the only one for the dipole-dipole coupling which remains is the central one in the principal axis frame. And that's root 6 times the dipole-dipole coupling constant, which for historical reasons is called small b. And that's given by minus some constants for SI units. And then these important terms, the products of the 2 magneto-gyric ratios, and then the inverse cube of the distance between them. So this equation then expresses the fact that the dipole-dipole coupling between 2 spins depends on the inverse cube of the distance. And actually that equation is the basis of molecular structure determination by NMR. If you can estimate dipole-dipole couplings, you can estimate internuclear distances. Yeah.
So what I'm trying to do the spin tensor, it's in the space tensor, the one it's for the NMR structure. Because that was the space one, and that one spin tensor seems like direct coupling to the
Yeah, well the idea here is that you have a spin operator which generates nuclear spin dynamics, but it's multiplied by a number which depends on the inverse cube of the distance. So the Hamiltonian is the thing which generates the spin dynamics, and that depends on both things, the space part, which depends on the inverse cube of the distance, and the spin part, which actually acts on the nuclear spins. So these two things can package together.
Have got any physical meaning? It expresses the fact that a magnetic field from one spin influences its neighbour. But it's not through the bond here.
Not through the bond, no, through space. So just like 2 magnets which are close in space sense each other. So one generates a magnetic field, and that magnetic field influences the other one. And when one expresses that rigorously, then you need these spin operators which have this type of form. So the dipole-dipole coupling then has, in principle, a relatively simple form. Just the m is 0 component of the space part in the lab frame multiplied by the m is 0 components of the spin part in the lab frame. The tensor only has an m is 0 component, but in the principal axis frame that's different from the lab frame. And that one non-vanishing component is proportional to dipole-dipole coupling constant, which is proportional to the inverse cube of the distance. So what we have to do in order to write down the interaction in general form is to get from the principal axis frame here to the lab frame there. At the moment they're in different frames. And that's done in this set of equations. Which maybe looks pretty nasty, but let's just unpick it. So we have the space part in the lab frame, the spin part in the lab frame. But we know the spin space part in the principal axis frame. So we need to multiply it by a Wigner matrix, which goes from the principal axis to the lab frame. And if you look at this equation here, you can see that you can pick out the chain. So we have a P here, which collides with a P here. The two P's collide and remove each other, and you're left just with an L, which is what you need here. And similarly, we have an M, which is summed over. They collide together, remove each other, you're left with a 0, which is what you need here. So these equations can be written down by inspection. So we have a sum over components in the principal axis frame. But it turns out that the only components in the principal axis frame, which is not 0, is the middle one, which is m equals 0. So of this sum, only the m is 0 component actually remains. So we can go from this equation to this equation, remove all the other components apart from m is 0, and then we get d2, 0, 0. That's the big Wigner matrix, the big D1. But the 0, 0 component is the same as the small Wigner matrix, the small D1, the reduced Wigner matrix, which only depends on the beta angle. And then we can substitute in the expression for D2, 0, 0, that's just a half 3 cos squared beta minus 1. And substitute in the expression for the spin operator, that's that. So we end up with an equation for the spin Hamiltonian for dipole-dipole coupling, which looks like that. Dipole-dipole coupling constant, depends on the inverse cube of the distance. A half 3 cos squared beta minus 1. That comes from the 0, 0 Wigner element. And then the spin operator. And that expression, if we want to, could be inputted straight into Spin Dynamica or some other program to calculate the NMR spectrum. Time for a break. 10 minutes. Right, so here we have, we went through step by step. We started with the equation which basically you read straight off the table. So let's maybe I'll just do the same thing over here. And then one says, okay, this is in the lab frame, but dipole-dipole coupling has its simplest form in the principal axis frame. So we need to go from the principal axis frame so I know it's rank 2, so I use the second rank Wigner matrix. Let the two summed index collide. So I get the 0 one. And then take the Euler angles going from the principal to the lab. And then the spin operator. So I have M, sort of self-destructing. And P self-destructing. Then one can use the property that A2JK, the mth component in its own principal axis frame, is just root 6 BJK and then delta M0. Where delta here is, this is a symbol called a Kronecker delta. It's often used in theory. Basically, delta AB is 1 if A equals B, and 0 if A not equals B. That's just a symbol often used in theoretical physics. So what it does here is that, what this means is that the component of the tensor with component m, it vanishes unless m is 0, and then it's equal to that. People seen Kronecker delta before? Anyone not seen it? Yeah. Okay, now you have. It's a useful shorthand for saying something vanishes unless a certain condition is met. So then if we want to do it very explicitly, we could write it something like this. Delta dipole-dipole coupling, root 6, delta M0, D2 M0, DL 220 JK. And then whenever you have a Kronecker delta, summed over the Kronecker delta, that means that the terms in the sum vanish unless m equals 0 in this case. So then I can just remove all the other terms. Like that. And then I can remember that I can use DL, the way the Wigner matrices work is a particular element, the rank L, the element m prime m, row m prime, column m, of the rank L Wigner matrix is e to the minus row index alpha, and then this reduced Wigner matrix beta, and then the m, the column element gamma. So if m prime and m are both 0, then these two exponentials are both 1. So it's just the 0 element for beta. So all of that goes in here. I should have been specific here about which principal axis system we're talking about. It's the principal axis system for the interaction, dipole-dipole interaction between J and K. Remember, for different interactions, there'll be different principal axis systems. So in general, one has to be careful to label which one. And then T20JK. And then root 6 beta JK. The 0, 0 big matrix element for rank 2 is just the important a half 3 cos squared beta minus 1. Which beta? It's the principal axis to the lab frame transformation for interaction JK. And then the spin operator, which is this thing over here, 1 over root 6, ZZ minus a half plus minus. So let's have a look at that a bit. So let's try and remember what we're doing here. We have a molecule with 2 spins, J and K, and they have a dipole-dipole coupling between them, and we're in solid state NMR now. We're imagining the molecule to be rigid. So there's no tumbling or anything, it's just held in place. And then we have a magnetic field. And what appears in the Hamiltonian is this expression, a half 3 cos squared beta PLJK minus 1. What is that beta PLJK? So we have the principal axis frame for interaction JK, which has its z-axis along the bond between J and K, or along the vector between J and K. And we have the lab frame, which is oriented, so its z-axis is along the magnetic field. Then the beta angle is the angle between the two z axes. So this angle is beta PLJK. What the equation says is that since the Hamiltonian for the dipole-dipole coupling depends on this function 3 cos squared beta minus 1, that vanishes when there's the magic angle. So the dipole-dipole coupling vanishes for beta PLJK is the magic angle. Yeah.
But the magic angle is the angle between the rotating frame and the magnetic field.
Okay, in this case, we're talking about a molecule. Okay, right now there's no rotation. So it's just like, suppose you have a fixed crystal, which you can do experiments with the crystal at different angles. So what this says, so there's no sample rotation here actually, it's just a fixed. But when the crystal is fixed, so that this dipole-dipole coupling, or the internuclear vector, is at the magic angle to the field, then the dipole-dipole coupling between those two spins vanishes. And you can think of this period, maybe pictorially, as imagining a d orbital. And then when the magnetic field is just at the node of that d orbital, then the dipole-dipole coupling vanishes. So what these equations are expressing is the symmetry of this interaction. So right now this is a static experiment. We're simulating here, or a static NMR experiment. But we can go a bit further. Suppose we're going to do magic angle spinning now. So the mathematics is now all there. So let's just develop the theory. We start in just the same way. So we're going to examine the case where, again, we just have a dipole-dipole coupling between two spins. So we have a principal axis frame. And we have a rotor frame. And a laboratory frame. The rotor spins around with angular frequency omega r. The molecules have random orientations in the rotor. So I'm going to express that with some Euler angles. Actually, in this case, I'll skip over the molecular frame. We don't need it, actually. We can go straight from the principal axis frame to the rotor frame. We could put in the molecular frame as well if we wanted, but this will do. So what this means is that the molecules with their vectors between J and K will be lots of random orientations with respect to the rotor. And then the rotor rotates with respect to the lab frame. So that depends on time. So this one you can say is random, and this is time dependent. And actually, as I wrote a minute ago, then the Euler angles for the rotor to Lagrange transformation, the alpha angle is just omega RT minus omega RT, if you look carefully. Then there's beta RL, which is the angle between the spinning axis and the field. That's the one which will be the magic angle when it's exactly set. And then the gamma angle, which doesn't matter, and we're going to just set it to 0. So that's basically the problem. Our task now is to write down the spin Hamiltonian for this setup. So principal axis frames of random orientations with respect to the rotor, and the rotor spinning with respect to the field. So we just go through the mechanism. It's just really turning the handle. So we start with the space part and the spin part. They're both rank 2 for this case. And because of the secular approximation, they're both in the laboratory frame. And now I can transform now. What I want to do is get this back from the lab frame through the rotor frame to the principal axis frame. So I just start turning the handle. First of all, I can go to the rotor frame. And then I can go to the principal axis frame. Principal axis frame, chain, M prime M. So I get here from the principal axis frame for interaction JK to the rotor frame, chain from the rotor frame to the lab frame, and spin operator. Then remember that for the dipole-dipole coupling in the principal axis frame, there's only the M is 0 component. So I can drop actually one of these sums. Okay. So these angles here, these are all random. Every molecule in the powder will have a different set of angles there. And omega RL is time dependent, according to this. So let's put that in, put the time dependence in. So if you remember, it goes e to the minus I alpha RL, m, sorry, minus I m alpha RL, and then the reduced Wigner matrix, beta RL. Then I would have a gamma RL term that is multiplied by 0, so it just vanishes, whatever it is. So I don't need a gamma RL term. And alpha RL is minus omega RT. So I have a time-dependent spin Hamiltonian, samples rotating, so it's time-dependent. I can substitute this in, actually, it's √6 times the dipole-dipole coupling constant, so let's do that. I have this Wigner function to get from the principal axis frame to the rotor frame. And then I have alpha RL, which is minus omega RT. So it's plus Im omega R times time. And then this Wigner stuff here. So this is the time-dependent Hamiltonian for a pair of interacting nuclei in a rotating solid. Now, to get a bit further, we have to make an approximation. We have to assume that we're spinning very fast. Essentially, this is another piece of spin dynamical theory, which I'm going to skip over here. But basically, if you have a time-dependent Hamiltonian, and it's varying fast enough, you can take the average. That's called average Hamiltonian theory. Which is a sort of a different topic, which by itself requires a few lectures. But the general idea is that suppose if you have a Hamiltonian which is varying rapidly enough, you can replace the Hamiltonian by its average over time. Which is theoretically plausible and can be proved within certain approximations and limits. This is what happens actually if the molecule's rotating in a liquid. We don't use the Hamiltonian, which is rapidly fluctuating because of the molecule's molecular motion in the liquid. We just use the average value. And there's a body of theory which leads to that, which I'm going to skip over, but let's just say that if we spin fast enough, and of course one always should really define what that means, but it's basically that, in this case, the spinning frequency, omega r, is much larger than the dipole-dipole coupling between the spins. With that approximation, and it is an approximation, but one which can be met by spinning sufficiently fast, then we can replace this complicated expression by its time average. Now, what is the time average? Basically, the time comes into these terms here. Now, so let's look at that. E to the I m omega RT, from Euler's theorem, that's cosine m omega RT plus I sine n omega RT. So the cosine function is basically a function of time, and the sine function is a function of time. If you average over time, the result is 0 for both of them. Except when m is 0. Because if m is 0, then this one vanishes, then you get sine of 0, but you get cosine of 0, which is 1. So we could write e to the I m omega RT averaged over time is delta m0. Again, that Kronecker delta again. So in other words, when you average over 0, the only term which survives is the m equals 0 term. And then that averages to 1. You get that? So then things get simpler. In this sum, after averaging over time, and I write down the average Hamiltonian over time, the only term which remains is m is 0. So I can scrub out all the terms with m not equal to 0, so I have d2 0 0 beta p r j k, and small d2 0 0 beta rl t 0 jk. And this again is a half 3 cos squared beta RL minus 1. This is the average, this is the magic angle, the angle between the rotor axis and the field. That angle is beta RL, and it goes to 0 and beta RL is the magic angle of tan square root of 2. So what's been shown here is that if one spins the sample in a rotor, and spins fast enough, that's important, then the average Hamiltonian, which to a good approximation governs what spins do, vanishes when the rotor is at the magic angle, and it doesn't matter what orientation the molecules have with respect to the rotor. It's the same independent, whatever this angle is, this term will still vanish. So you see, when you have a static solid, then you have to get the molecule at just the right angle with respect to the field to make the dipole-dipole coupling vanish. But in this case, you don't have to get the molecules at the right angle with respect to the rotor, because this term vanishes. And that's the principles of magic angle spinning. So the maths may look complicated, but what this comes down to actually, if you think about it, all of this mathematics will be exactly the same whatever the space part of the interaction is, as long as it's rank 2, it will be the same mechanism. So one can basically look at that table, and whenever one has rank 2 for the space part, one can deduce immediately without doing any calculations that if you spin sufficiently fast about the magic angle, the average Hamiltonian for that interaction will vanish. Okay? Any quick questions at the end of that? Yeah.
How would you be able to simulate that spin dynamic?
Well, basically, you simply is maybe wrong. You would simply, you could use the average Hamiltonian, so you could make this approximation already, and then simply write this equation in. And there are spin dynamic objects for the big matrices and for the spherical tensor operators. If you want to calculate the time dependence, you can write this equation in, where you can give it a time dependence. And in a way that will be, there's a way in spin dynamic of specifying a Hamiltonian which is time dependent. So again, it's just a question of writing the equations in. But that's maybe a topic for a different time. What I could maybe show, we'll see next week, maybe there's enough time to actually write these programs. I'm not quite sure how Spinach handles this. I think that programs like Spinach or Spin Evolution or Simpson, which are set up for doing solid state NMR, they will basically, having specified the spin interactions and the angles, they will basically set up all the relevant Hamiltonians without you actually having to write any equations, which is nice, but this shows you the sort of inner workings of it. Time for us to go.